Okay guys, well, welcome to today's lecture. We're going to talk about stochastic processes again, in particular random walks. So that's going to be the major topic of today. Random walks, as well as basically their asymptotics, which we didn't do last time. We're going to recall the moments, expectation, variance, and so on, with or without a drift. That's going to be important. So that's from lecture 4. But I need that result, so I'm basically just quoting it. I'm going to also address another representation because I want to address basically the variance of sums that were created from random walks. And since they're correlated, they're not supposed to have the covariances, so I need another representation for that. Then I'm going to consider basically the sample moments of random walks, especially basically their expectations and variances in particular. Okay, so we're going to calculate expectation and variance of the sample mean taken from random walks. We're going to show that basically as estimators, the sample mean and the sample variance are going to be inconsistent. Okay, so you cannot estimate the variance basically using those. And we're going to look at the asymptotic distribution, which we'll find it is not going to be normal. So that's basically that. And I'm going to introduce you to basically the major concept, which is the Brownian motion. Okay, I'm going to address this basically looking at so-called rescaled random walks. Okay, or diffusively rescaled random walks. That's the correct term. Which basically leads us to the functional central limit theorem. So that is actually a general version of the central limit theorem, but was generalized in the 1950s or so, if I recall it correctly, which is called Donsker's theorem. So that's basically the central result of today. And after that, yeah, we'll basically see what the implications are, among others. So yeah, that's basically what we're going to do. Okay, so that is it. Well, that's going to be the major issue. Okay, so Donsker's theorem is going to be the major issue. Now, let me recall basically what the random walk is, or in particular, basically what the moments are. So the random walk denoted by Z, okay, that is a stochastic process which can be expressed like this. So you have a previous observation plus the current observation of the noise. We talked about it basically last time. We saw that the process was not stationary, among others, right? And of course, we assume in this case that the noise is IID, all right? So that's a very strong assumption. It works also if it's not, but at least that has to be uncorrelated, all right? So, but we're going to basically make it a little bit easier. Now, based on that, okay, we were actually developing, you know, the previous is the recursive formula, and we basically were looking at the explicit formula given a starting value. So we're going to look at the some starting value. And then you have the cumulative sum of the noises. Now, the cumulative sum of the noises is going to be, or was, the partial sum process. Okay, so keep in mind, guys, that those two are equivalent. All right, so that's basically pretty much it. Now, there is actually, that's the same thing, so it's not going to be different. Now, the issue is we're going to introduce it also drift parameter. So what happens if it basically evolves around the constant? So then, of course, you'll have, well, I don't know, people can't read, goddammit, so sorry, I'm just, okay, please do not disturb, and then people open it anyway. I need a gun. All right, anyways, okay. All right, so that's going to be the parameter. This is delta. That is basically a real number. It can be anything. If it's 0, then you have basically just a regular random walk. And then, of course, if you accumulate that, it's going to be delta times t. So keep that in mind. Okay, so there is going to be a linear trend in data. If you sum those basically up, it's going to be different. All right? Okay, so that's basically, that was a topic of the 4th lecture. And now we're going to look at basically, also, we're going to review the properties based on that. Now, regarding the partial sum processes, as I told you before, that's the process which is generated by the cumulative sum of those noises. And we were also looking at the moments. So we were looking at basically expectation and so on. So the expectation was basically the expected value of the starting value. Now, if the starting value is assumed to be a constant, most of the time it's assumed to be 0, then the expectation is going to be 0. The variance is actually not. So the variance is time dependent, as you saw. It's going to be actually, so if basically the starting value is assumed to be a constant, at least almost surely, then you have a linear dependency regarding the variance. Okay? It's actually also proportionate. Now, and thus this process can no longer be stationary anymore. So even with or without a drift, it don't really matter. The variance is time dependent. It doesn't basically, it's not going to get away. Now, the autocovariance that's something I don't need here, but I was doing that anyway. So that was basically the autocovariance of the random walk, the minimum of t versus t plus h. So if h is basically greater than 0, which means that you're looking to the future, then the minimum of that is going to be t times sigma squared, which is just as large as actually as the variance. So if you ignore the starting value, right? And but it's not, then basically it's going to be just, I mean, t minus, so t plus h if h is negative, so you look back. And this means that, of course, the autocorrelation will converge at least to 1 as the sample size, or let's say as time increases, right? That's basically also another issue. For that, you would just simply do autocovariance divided by the product of the standard deviations. And whatever the standard deviation is, again, if you ignore the starting value, that's basically just going to converge to 1, no matter what, all right? Which is kind of weird, right? Anyways, now what I also didn't mention explicitly, but the increments are actually equal to the noise, right? The noises are the increments because you sum up the process. So you would basically just do that, and that's basically what you have. So if you go this way, this is called differentiation. And if you go basically, I mean, the random walk, I ignore the starting value. So if you simply set this equal to the partial sum process, right, then that's going to be called integration. So that's basically integrating the process, and that's called differentiation of the process, right? The increments are equal to the noises because as the process progresses, there's always going to be some additive noise coming after that. So that's basically what the random walk is. As you can see, it's no longer stationary. No matter whether it has a drift or not, it doesn't really matter anymore. Of course, if it has a drift, then it's going to be, for the mean, is also going to be time dependent, but that doesn't change anything. All right, so again, I mean, it does change because I have also a linear trend in data, but it's not going to be stationary. So even if you would eliminate the trend from the data, the trend would not go basically away, just simply. All right, because, I mean, the trend would go away, sorry, but stationarity cannot be achieved. All right, so it will not be stationary around the trend. Apology. All right, guys. So that's basically lecture 4. So keep that in mind, guys. I need the expectation and I need the variance today. So that's why I was recalling it. Okay? And that's what we're going to analyze within the asymptotics of the random walk, especially regarding the sample mean of the random walk, which is going to be singled out. Okay? Now, regarding asymptotics, the first thing that I'm going to show you is that there is going to be convergence in probability for the random walk if you multiply the random walk by 1 by t, or you're dividing it by t. That's going to converge in probability. And if it's basically the standard random walk, then it's going to converge to 0. I'm going to show that in a moment, so that's not going to be a big deal. Okay? So at least, you have that type of asymptotics. Again, so that's basically what it will be. And the second is I'm going to show you that the expression 1 by the square root of time, basically, or time component, times the random walk will converge in distribution to the normal distribution. Now, it's not going to be the standard normal distribution because I wasn't standardizing it. This is the variance of the noises, right? So that's going to be basically here. And I'm going to show you that in a moment. So based on the central limit theorem as well as the weak law of large numbers, this was considered actually our lecture 2 or lecture 3, I think, maybe lecture 3 or so, if I recall it correctly. Not sure, I've forgotten. Anyways, okay, so we have already done that. But I'm going to recall the major results. So regarding the weak law of large numbers, that involves actually convergence in probability, whereas the central limit theorem actually involves convergence in distribution. So whenever basically those two are coming up, I would basically recommend to try to use those. Okay, so weak law of large numbers is a very common one. I mean, even in economics, right, or econometrics, okay, so you would basically, you would need to use it. We were talking about it, so that's why I was introducing you to it. Now, and I'm going to make an exception here. This is going to be true if actually the starting value is going to be 0 almost surely. Let me say this, it's going to be also true if it's not. Okay, so it's not going to be a big deal whether this is not going, whether this is 0 or not, because that will disappear, at least almost surely. Okay, so if I assume that it's going to be 0, it doesn't change anything. So the issue is just to remind you, if you don't need, if you don't use the assumption, okay, that is going to be 0, at least almost surely, then it's going to disappear anyway, no matter what. Okay, so it will disappear. It's not difficult to justify this. Okay, so I will simply just ignore the starting value, and I will, if I simulate samples, which I will, I'm going to assume that it's going to be just 0, actually. All right, let me check whether it's working. So, but it seems it does. Okay, so sometimes it just basically interrupts. Now, if the thing has a drift, okay, then this is basically adjustment that you're making. Okay, so simply just, you know, centralizing. That's called centralization, by the way. So if you actually subtract their expectation. Again, I did not include the starting value in here because it would be just bigger unnecessarily. Okay, so, and who cares about the starting value? I mean, the process is starting at some point somewhere. Congratulations. Okay, so again, it's not, I mean, you be thinking that, okay, what about that? But basically it's not very hard to justify this. Okay, so even if it's not true, it's going to disappear. And yeah, so the question is how to do it. And I'm going to start by basically looking at convergence and probability. So let's assume that, again, the starting value is 0, at least almost surely. Then what? Okay, I mean, of course, then the random walk degenerates to just a partial sum process, right? So that's basically what will be, because it has practical issues in terms of I want to make the proof easier, okay? But if you don't assume that, it's not, I mean, it's not going to be necessarily false. All right, now we're going to recall the vehicle of large numbers. So the vehicle of large numbers, again, it's basically involves, you know, the issue if you have a sequence of random variables which are IID, where their expectation is mu and their variance is sigma squared, then it will basically, claim that, I mean, the vehicle of large number does claim that their sample mean. Okay, so what you have is actually their sample mean. I'm sorry about this. It's going to be just, you know, a little disturbing here. That the sample mean converges in probability to the mean of their corresponding values. Okay, again, I apologize for that one. Okay, so that was basically the vehicle of large numbers. Now, how would you establish that? You just need to actually make sure that 3 things are satisfied. Number 1, if I basically calling the members, okay, they all have the same expectations and they're all finite. So the expectation must be finite. Number 2, the variance must be finite. And number 3, they must be at least uncorrelated, which they are, because they're independent. So if they're independent, they're also uncorrelated. I mean, they will be, because I'm talking about those guys here, all right? So I'm talking about the noises, not the random walk, because we don't have basically that sum. Okay, so that means basically looking at the sample mean of those noises will actually converge in probability. So based on that, because noises are IID, all right? So this means that their sample mean will converge in probability to their respective expectation, which is going to be 0. That's for sure. Okay, so based on actually the vehicle of large numbers. And that's basically what I'm going to use here right now. So you're going to see this. Okay, so let me remind you, I'm going to look at the sample mean of the noises. And the sample mean of the noises, however, will satisfy the vehicle of large numbers. It does. Okay, so that thing will converge in probability to its expected value, which is actually 0. Okay, because the noises have 0 mean. So the sum of those zeros is going to be 0 as well, and 1 by n is not going to change it. So you have basically 0 as the expectation, right? So this is something that you can already use because that satisfies the vehicle of large numbers. It's IID, so it's the same thing, all right? And yeah, so this is basically what it does. And I was not mentioning that basically if you compare that, so if you're starting from here, that this expression is equal to that, which I just ignored, right? But that's still true. Okay, so if you look carefully, you're going to see this. Because all you would need to do to get there is just to divide the random walk by t. So you have basically the random walk by t. So then the sum would be divided by t as well. You see? That's basically how it works. Okay, so since the sample mean of the noises satisfies the vehicle of large numbers, so does 1 by t times the random walk. Because the random walk is the cumulative sum of those noises. And if you divide the cumulative sum of the noises by the size, then of course, I mean the sample size of the noises, then you would basically get the sample mean, right? So that's basically it. Okay, guys, I hope you understand this. Now, recalling the central limit theorem, it's not going to be basically, different than that. So you can see that basically how this works. But it was a little bit different in that sense because you would need to standardize differently. So just recall that the variance of the sample mean, I'm talking about those random variables, is equal to sigma squared by n. We did this actually extensively. So you would need to standardize by sigma by n. Okay, now I'm keeping sigma out, so that will converge distribution to the normal distribution with mean 0 and variance sigma squared. Okay, so that's basically what it's going to be. It's not going to change it. All right, so that's actually it. All right, but just please recall that it's actually, what we had done is actually the square root of n times the sample mean minus mu divided by sigma will converge to the standard normal distribution. Okay, and I wanted to take basically sigma squared out from the denominator, so put it back in. So if I basically delete this, and yeah, I need to put it back. Okay, so the standard deviation, then it's going to appear, it's going to come back here as a parameter for the variance of the distribution to which basically, the normal distribution to which actually this test statistic converges to. Okay, now, and the sample mean of the noises does that. So here you do that actually. Okay, so what you need to do is this. Okay, I'm going to show you that 1 by, or the square root of t, which is the square root of the sample size, times the sample mean of the noises. The sample mean of the noises is 1 by t times actually the partial sum process. And then you would subtract basically the expectation, and the expectation would be 0. And that's it. Okay, so you can see clearly, after that, when you look at that one, so I'm going to basically was using the central limit theorem for that, because this thing will converge to the normal distribution with mean 0 and variance sigma squared, obviously. And that thing, the orange part, all right, is equal to that. You can check it out for yourself. So when you basically multiply, you might not see this, right? But as you see, the random walk is equal to the partial sum process, okay? And the square root of t times 1 by t equals 1 by the square root of t. Okay, so if you take that times that, you might not seeing this, right? If you take the square root of t times actually 1 by t, then you will get basically 1 by the square root of t then. And you can ignore 0. I was just basically using 0 just to demonstrate that the expectation of the noises is 0. If it would be different, then I would basically use that parameter also. That's it. Okay, so that basically is going to converge according to the central limit theorem to the normal distribution with mean 0 and variance sigma squared, and so does that one also. That's it. You understand the point? So that's basically illustrating the proof. And yeah, so then you have at least asymptotic normality, but not for the random walk, actually. So the random walk is not going to be asymptotically normal. It's going to be 1 by the square root of t times the random walk, which is going to be asymptotically normal. So you need to do a linear transformation all the time, every step of the way, basically when you're addressing it. Okay, and that's basically what it would be. And the same result is going to be true if there is a drift. So if there is a drift, okay, then you would basically just a different test statistic. Because then you would simply, when you basically rearrange this equation and you simply subtract the linear trend, okay, then you would get the partial sum process, and then you would start from here. Okay, so you would start from here, and then, you could take basically the test statistics accordingly. So I'm basically centralizing, that's how it's called, centralizing those test statistics prior. So this will going to be basically satisfying the weak large numbers. And this test statistic is going to be satisfying the central limit theorem accordingly. Okay, because that expression did not change, right? That's it. So it's not a big deal. Okay. I will take that and I will basically make an exercise out of this. I'm about to editing the exercises, so you're going to see them very soon, and that will be one of them. So you will need to just basically show that one, applying the weak large numbers and applying the central limit theorem within that context, okay, of a random walk. Now, let me continue. So we're going to look at the sum right now, okay? And for the sum, I need a new representation, because what I'm going to do, so you see basically the sum of the random walk, right? So the sum of the, that's going to be the sum of the partial sum process, right? So you sum up the noises and then plus you say the random walks as well, because what I'm going to do after is I will need to look at the sample variance of the random walk, and I want to analyze, for example, the expectation of the sample variance, or the sample mean, by the way. Now the issue is this, the variance of a sum is not going to be actually equal to the sum of the variances if the sum ends are correlated, if the sum ends are correlated, which is the case here for the random walk. Okay, I mean, the autocorrelation is going to converge to 1. So what do you think where basically those autocorrelations are coming from? If they're not autocorrelated, they are. Okay, so but that's going to be the issue here. Anyways, okay, so I will need to analyze this, and I need another representation. Okay, so I'm going to make sure that you understand this. First off, again, keep in mind, so if you assume the starting value to be 0 almost surely, then you're going to see that basically the random walk is always equal to the partial sum process summed up to actually up to time t, of course. So when you start at basically at the first, let's say, observation, let's call it the observation. If it's not, then basically it's a random variable. That's going to be simply just the first noise, and there is no other. If you take the second observation, that's going to be the sum of those noises up to that, okay, and there is no other. And then, of course, you're going to end up with the last one, which is basically the sum of those noises up to time point n, and there is no other. So that's basically how you break it down. And you need to find that. Now, of course, they have something in common. So, for example, how many times do you find the first noise in the sum, and that's going to be n times. The second is going to be n minus 1 times there. The third is going to be n minus 2 times, and so on. And the last one is just going to be 1 times. So that will be basically just go down when you're counting it. Okay, so that's basically what I'm going to do. So you have n times the first, then you have n minus 1 times the second noise, and then you have n minus 2 times the third, and so on. And then you have basically 1 times the last. You understand why? Okay, so that's actually how this evolves. Okay, so here you have it n times, here you have it n minus 1 times, and if you continue, you have the last one just 1 time. All right, so actually this is basically how you're rearranging it, and that's good because those are not autocorrelated anymore, right? So I was eliminating the autocorrelation, but I would need to put them some weights, okay? And that's what I did. So when you basically look at the result, which again is going to be, I mean, if I have basically a summation index, you can also change it if you like, I times basically the noise at time point n plus 1 minus I, which might not be intuitive, but if you basically reverse it, you'll see. So if I is equal to 1, then this is going to be 1 times epsilon at point n plus 1 minus 1, which is basically epsilon n. Okay, so that's basically the first sum end. Here it is. Okay. So as you see, it starts from behind, but it doesn't really matter. And if you look at the last sum end, the last one, if basically you set I to be equal to n, that's going to yield n times epsilon at time point n plus 1 minus n, which is basically at time point 1, by the way. Okay, and that's here. Okay, and so this is basically just reversing it. Again, the reason why I did that is basically I want to analyze the variance of a sum, but as you see, if I express it by some weighted sum of those noises, then those noises are not going to be autocorrelated anymore, by definition. Noises are not autocorrelated by definition, but basically the random walks are. Okay, so those are autocorrelated. I mean, those are correlated, basically, or they correlate with each other. I mean, you can call it autocorrelation, right? But actually, the noises don't. Okay, so that's why if I take that, and if I want to basically take the variance of that, that's just going to be the variance of the sum, which is the sum of the variances after all. So that's my purpose. Okay, and if you include the drift parameter, okay, so if you have the drift, I mean, it's not going to change that much. Okay, now if you take the random walk with the drift, here you can see it. Okay, so that's basically what it is. Okay. Then again, so you have delta times t up to that time point. So if you're basically looking at the first point, that's going to be delta times 1 or simply delta. Then for the second, it's going to be delta times 2 and so on. And for the last, it's simply just going to be delta times n, which is here, okay? And yeah, so then after that, basically, you need to just basically find the sum of the 1 plus 2 plus 3 plus 4 plus blah, blah, plus n, right? So the sum of all numbers from 1 to n. Now there is a formula to this. Okay, I'm not sure if you're familiar with that. That's basically arithmetic series. Arithmetic series, so the sum of all numbers from 1 to n is going to be n times n plus 1 divided by 2. If you're not sure about that, why? You could simply use complete induction to prove it, but that's something you can pick, okay, because you have delta times a sum from 1 to n, which is actually delta times n plus 1 by 2. That's what it's going to be, okay? So if I apply this, then I'm going to get that. Basically, just to rearrange again, I'm taking that out from the sum, and that's going to end up here. So that's also what you're about to see. You understand the point? Again, this is just, you know, reparameterization, if you like. But that's, if you take the variance of that, it's not going to change it because the variance does not depend on additive constants. So there is not even a necessity for considering the variance of actually a random walk with the drift. You could also simply just take without it because the variance, again, of a linear transformation does not depend on additive constants. Okay, but again, I'm going to use that later on. So now I'm going to look at the sample mean and basically, and the expectation of that as well. The sample mean of the random walk is going to be the sum of the random walks time basically by the sample size. I mean, I'm calling that sample size, so n is going to be a sample size, so that's basically what the sample mean is, aka the arithmetic mean. And I will need to basically analyze this a little bit because I'm going to show you later on that the sample mean, in contrast to the sample mean of the noise, will not satisfy the weak law of large numbers, and it will not satisfy actually the central limit theorem either. But not just that, it's not going to be basically consistent estimator for the expectation. I mean, if there is any, right? Because, I mean, if there is no drift, there is none, but it's not going to be actually consistent, nor it's going to be, I mean, since it doesn't satisfy the weak law of large numbers, it cannot be actually considered to be a consistent estimator. But again, so I'm going to put it back here, and yeah, so just declaring it, and I'm going to calculate the expectation of it. So the expectation of the sample mean, I was basically doing that last time, the expectation of sample means of something else, but this time around, I mean, it is the same principle. You have a linear transformation. This is a random variable. So the sum of random walks is random, and thus it is actually a linear transformation of it. And when it comes to linear transformation or their expectations, the expectation of a linear transformation is equal to the linear transformation of the expectation. And then you can simply just bypass the sum operator by the expectation operator in addition to that, because the expectation of a sum is equal to the sum of the expectations. And since these things are zero, by the way, the expectation of the sample mean of the random walk would be zero after all. Okay, so that's going to be zero. So the sum of those zeros is zero. It's not a big deal, right? So that's it. Now, when it comes to a random walk with the drift, that's going to change a little bit. There is going to be time dependency regarding it. So because the expectation of the random walk is different now. That was delta times t, right? So then you take out delta, which I did, and then you have the sample mean of these t's. And then you come back again with that formula where you sum up basically all numbers from 1 to n this time. Okay, so that's basically the formula that I was showing you prior. So delta times 1 by t will stay. And then I'm going to take that calculating by the previous formula, which I also used. So the sum of all numbers from 1 to n, which is n times n plus 1 divided by 2. So you simply just take that. Again, you can look those things up if you like, but you will not need that for an exam, just for the records to see how basically I'm cracking it. And then you have basically the same thing, n times n plus 1 divided by 2, right? And that's it. And therefore, you could simply just cancel n after that. Okay, so you can take it out from the fraction, so you're left with delta times n plus 1 by 2. Now, the thing is this. I'm going to basically address this. And that's basically what it will, that's why it's going to be blown up. Because this is going to converge to, I mean, it's not going to converge, but it's going to diverge, actually, as the sample size increases. You understand what I'm saying? And that's not supposed to happen if you want to estimate, basically, the expectation, or at least this parameter consistently. Okay? That's basically not going to work. So the linear trend cannot be estimated directly, at least not from the sample mean of the random walk. You would need to adjust this. Okay, so the arithmetic mean is actually a good estimator if the process is stationary, for example, but it's not going to be a good one if it's not in general. Okay, so that's basically what I'm going to demonstrate later on. Not now, but later on. Okay, but keep that in mind, basically. That's the reason why I was doing it. Now, I'm also analyzing the variance. And for the variance, I was using the representation that I did. So the variance of the sample mean, which is, again, the variance of the sample mean as you said it. Now, if you want to take that out from the variance separator, you would need to square it. Because as far as you remember, if you take the variance of a linear transformation, that's not going to be the linear transformation of the variance. Okay? First off, it doesn't depend on additive constants. Now, there is no additive constant here, so you would not need to do it anyway. But second, there is a multiplicative constant. Now, if you want to take that out from the variance separator, you would need to square it. So 1 by n squared is going to be 1 by n squared, right? You understand the point? Okay, so that's basically what I was doing. And then you have the variance of the sum. And here it comes. So if you basically do that, the variance of a sum is not the sum of the variances, because, again, those are correlated, okay? So that's a point. So I was basically relying on the previous representation, but thank God I was preparing it. So the representation that basically you do, I mean, okay, 1 by n squared is going to be n to the power of -2, which is actually quite understandable. And then what happens basically to the variance of the sum? Now, before I take it, I would need to remind you that basically the variance of the sum, or the sum, sorry, was simply just this expression by the weighted sum of those noises. So we were looking at prior. And again, the reason why I was doing that is basically now those summians are not autocorrelated. In contrast to those are, okay? Those are, okay? But if I basically break it down and rearrange it, then it's not going to be anymore. You understand what I'm saying? So therefore, that's basically boils down to, and then I could continue, because then the variance of a sum is going to be the sum of the variances. You understand what I'm saying? So you can simply just bypass the variance operator by the sum operator now. But the issue is, what is going to be the variance of that? What I'm going to do in addition, and as you see, there is a linear transformation. Okay, so this is a linear transformation of the noise. The noise is random. And then, of course, I is a constant. Of course, it changes because that's a summation index, but it doesn't change randomly. You understand what I'm saying? So you could take that out from the variance operator. And if you take the variance of this expression, it's going to be I squared times the variance of the noise. And that's basically what I'm going to end up with. Okay, so you can take that also out from the variance operator. I did 2 steps here. Okay, the variance of a sum is, in this case, the sum of the variances. And since basically you're having a linear transformation here, I want to take it out from the variance operator, but you need to square it as usual. So that's going to be I squared times the variance of the noise. Now, how would you take that? Now, the variance of the noise is sigma squared. That's, you can take it to the front. And then you have actually n to the power of -2 times the sum of the squares. Now, you can simply also address what the sum of the squares are. There is also a formula to this. So if you're not sure about that, I will just give you again, but you will not need it. So don't worry about it. So don't try to, I need to look it up myself because sometimes I tend to forget it anyway. So the sum of the squares from the first to the nth square is going to be n times, it kind of resembles to the previous one, n times n plus 1 times 2n plus 1 by 6. Okay? Now, if you're not sure where 6 is coming from, don't worry. Okay? You don't need to. Okay, so you can look it up and you simply use complete induction to prove that, which I'm not going to. So I'm not going to waste time on this. You could this is simply, it's not simple. It is not difficult, but it's just going to be some arithmetic. Now, what I'm also going to do is I'm going to take that, which is actually there, and I'm going to multiply it by n to the power of -2, which is 1 by n squared. And then I'm going to rearrange that stuff. So keep that in mind. When you do it, take that and multiply it by 1 by n squared, which is going to be the final result. And then, of course, you have times sigma squared. So sigma squared times 1 by n squared times this expression, which you just saw. And I'm going to take that. So if you're basically using it, okay, now 1n is going to be canceled and other is going to be there because you multiply it by 1 by n squared. So that's basically what you end up with. So the final result is going to be n plus 1 times, in brackets, 2n plus 1 by 6, okay? Now, whatever that is, again, it doesn't really matter. 6 times n, of course. Okay, I forgot that. Sorry. But whatever that is, this is going to diverge too, okay? Because in the denominator, you're going to have n squared and in the numerator you're going to have n, right? Okay, so n squared by n is going to converge, and thus this is, I mean, it's not going to converge, sorry, so therefore this is going to diverge. So the variance of the sample mean is going to diverge, and that is the main reason why that will not satisfy actually neither the weak law of large numbers nor the central limit theorem. You understand the point? Okay, so that's going to be the issue here. And this is something I need to address, okay? So if the variance diverges, then you cannot do it, okay? So simply, I mean, basically both, neither for the weak law of large numbers nor for the central limit theorem. If you put the drift in there, it's not going to change anything because this is an additive constant, and the variance actually of a linear transformation with an additive constant in it will not depend on that additive constant. I talked about that actually at the beginning, right? So when you basically do that one, there is, again, so it's always going to come down to the basics, guys. Anyway, so it's not going to change. That's going to be it, okay? Because the variance of a linear transformation will not depend on an additive constant, and I will talk about it. It only depends on the multiplicative constant, but there is no random variable to multiply that with, so it will basically just be the same. Anyways, okay, what I'm also going to look at, yes, yes, sure.
Go back.
Sure, yeah.
Yeah, just a small one. We can do this operation with the summation sign because those epsilons are...
The noises are not correlated, yes. Yes, they are. Noises are IID. Today, there are IID all the time, okay?
No, I mean, this is the explanation why...
Yes. That's the reason why basically I was able to, so in this case, and that was a problem that I had, so that's why I was introducing basically to another representation of the sum of the random walk, because the summands here do depend, I mean, they have, you know, they have autocorrelations, right, which are not zero. So then I would be struggling with the covariances, but I don't want to have them. So if I use a different representation, I could basically go around that. So the variance of a sum will be the sum of the variances, at least, but not for those, but for those. You understand what I'm saying? And the sum of, basically the sum of the variances will be the sum of the linear transformation of that variance. So in addition, I was taking out I by squaring it from the variance operator. So that's basically it. It's not that difficult, guys. So I'm always using the basics all the time. Means, expectations, linear transformation, all that stuff, okay? Every time, okay? It's just a different context. Anyway, okay, so I'm going to talk about it, and basically I will also look at the sample variance, but before I do the sample variance, I'm going to consider the sample, basically the second sample moment. The second sample moment is actually the mean of the squares, the sample mean of the squares from those observations. Because when you look at the sample variance, okay, so the sample variance is going to be the mean of the squares minus the square of the mean. Maybe you remember that formula from statistics, right? I mean, there is also the mean of the square deviations, okay? So the sample variance, again, so let me recall that one so you're not sure, basically, but I'm going to decompose that into two parts. So the sample variance is going to be actually the mean of the squared deviations, okay, of the observations with respect to the arithmetic mean, which is actually the mean of the squares minus the square of the mean, right? That's basically it, okay? So I'm going to focus on that one first, which is called the second empirical moment, or the second sample moment, which is actually the mean, this is it, all right? So the sample moment, so the mean of the squares. Okay, and then I will put it together for the sample variance. So it's not going to be the sample variance yet. It's just the second sample moment, but I'm going to try to build it up. So that's step number one. Okay, and then I will basically include it. Anyways, so I'm going to look at what happens basically to the expectation of that, because that's what I'm interested in. And I will show you that that's going to diverge as well. So that's the only essence here. So you will not be able to actually be able to estimate the variance from the sample variances when it basically you have a random walk, and that's basically also typical for a non-stationary time series. So that's a lesson to learn here. Okay, now anyways, okay, so I'm going to basically, okay, taking out basically 1 by m from the expectation operator is going to end up with the 1 by n times the expectation of the sum. And since the expectation of a sum is going to be the sum of the expectations, whether they depend on each other or not, this is simply just going to be the sum of the expectation of the squares from the random walk. Okay, that's it. Now, how would you get that? And there is actually an alternative because you can basically crack it. Keep in mind that the variance of a random variable, I'm going to call it y, so you not feel distracted, is the expectation of its square minus the square of its expectation. Okay, so as you see, this is here, okay? And I'm going to change that. So I'm going to replace the expectation of the squares by the variance plus the square of the expectation. That's it, okay? So that's what I'm going to do, okay? Because the variance is equal to the expectation of the squares minus the square of the expectation. So that's what I'm going to use here, okay? So again, I was mentioning that before. I'm going to substitute that by the variance of the random variable, not by the square, and of course, minus the square of the expectation. Now, why is the expectation missing? Because the expectation of the random walk is 0 if there is no drift, okay? Because that would be actually corresponding to the starting value, at least almost surely. You understand the point, okay? So that's why it's missing. So the variance is going to be equal to the expectation of its square. And I have basically looked into the variance of the random walk last week. Lecture 4, we were doing that. So I was basically getting those results back. Okay, so you're going to get 1 by n times the sum of those variances. Now, again, the variances were sigma squared times t. Remember that? Okay, so that was last week. Okay, so again, I'm just basically, it's not difficult, guys, to put those things together. It's just a lot of pieces, I have to admit, but we were doing that already. Okay, and I wanted to do it basically in a very structured way. And then you take that sigma squared from the sum, because if you multiply every sum n by sigma squared, you end up basically by multiplying the sum by sigma squared. So the sigma squared times actually, and then I'm going to do it again. So you have 1 by n after that times the sum of all, again, so I was doing that already here. So 1 by n times that, because that's basically what the sum would be, is going to be sigma squared times n plus 1 by 2, by the way. So that's it. Now, this is going to diverge, okay, as you see. So since it's going to diverge, there is no way for the sample variance to satisfy the weak law of large numbers. That's the point, okay, because that thing is going to diverge. And you will not even need to care about basically, but that's basically the strongest statement that I can make. What happens to the rest is not that important. So if the second moment diverges, or the sample expectation of the second moment diverges, the sample variance can longer satisfy the weak law of large numbers. I'm going to summarize that also, but that's basically what I'm going to. Okay? If there's a drift, now, well, okay, if there's a drift, it's going to change a little bit, but it's still going to basically diverge. Okay? So that's a major issue. Okay? Now, again, if you take the expectation of the squares, in this case, that's going to be the variance plus the square of the expectation. Okay, and since basically the expectation is not 0, the square will not be 0. Okay, and then I'm going to split the sum. So that's going to be 1 by n times the sum of those squared expectations. And what's the expectation? And what is the expectation of the random walk? The expectation was delta times t, if there is a drift. So the square of that is going to be delta squared times t squared. All right, so that's basically what we'll have. Okay, simple as that. And then you do the same thing again. Now, again, what happens to this? I'm going to take us delta squared, and then you have basically the sample mean of the squares from 1 to n, for which I'm going to use basically the formula again, where you would sum up the squares. So this is n times n plus 1 times 2n plus 1 by 6, right? So take that, multiply it by 1 by n, so you're going to get rid of 1n, and that's what you end up with. Okay, but again, it doesn't change that much. I mean, it will change basically the expectation of the second sample moment, but, well, it's still going to diverge, okay? It's not going to, so this is not going to get away, right? So, in addition, it's even worse, right? Because, you know, that has the rate n squared, and whereas this is going to be basically by the linear function n. You understand the point? Okay, so it's even worse. So that's also diverging even faster. If it has a linear trend, the expectation of the squares is going to diverge faster. than without it, but it's still going to diverge. So whether it's diverging faster or not, who cares? You blow it up, right? You blow it up, you blow it up, you blow it up faster. Congratulations, okay? So, I mean, why would I basically waste my time on that? Now, if I put it together regarding the sample variance, okay, which I would need to look at. So, the sample variance is the mean of the squares minus the square of the mean. Now, before I do so, okay, I will look at basically the expectation of the sample variance. So the expectation of the sample variance, you just need to basically put in minus the square of the sample mean into those expectation operators. And that's going to be, again, the expectation of the, I mean, we talked about that, so we don't need to do it again, okay? I'm building these blocks already. And that will be basically the expectation, so minus the expectation of the squares, not the square of the expectation, okay? Now, what is the expectation of the square? This is going to be the variance plus the square of the expectation of the sample mean of the random walk. You understand what I'm saying? And we did both, okay? So there is a lot of things going on here, right? Okay, so that was done, okay? But again, I'm going to do it again. And that is, again, the expectation of the squares is the variance plus the square of the expectation, and then since there is a minus here, this is going to yield minus the variance minus the square of the expectation. But that is, okay, so that is going to be 0, right? Because the expectation of the sample mean of the random walk is 0 if there is no drift. If there is, then you would need to adjust it, okay? But I was not doing that anymore because I was sick and tired of that shit, sorry. So again, there was too many variables and parameters and all that stuff because I'm not even interested in that anymore. Again, if I basically can confirm that the expectation of the second moment, of the basically second sample moment diverges, then so does basically the sample variance. Okay, but I want to basically just make that statement at least so you understand what that is. Okay, so this is not going anywhere. Okay, and again, I was not even addressing the variance of the sample mean of the random walk. Okay, because all I'm caring about is asymptotics now. Okay, so that's going to diverge. Okay, so who cares basically? I mean, that's not going, the others will not eliminate that. So who cares basically what the rest is? You understand what I'm saying? I'm being pragmatic here right now. Okay, but maybe I'm going to give you an exercise where you would need to put all these things together, but it's going to be too huge, too big. You know, so wow, okay, it's going to diverge. So, okay, it's going to diverge faster, you would say. Okay, well, it doesn't change that it's going to diverge. Okay, so it will not satisfy the vehicle of flush numbers. Okay, the sample variance will not satisfy, of the random walk will not satisfy the vehicle of flush numbers. Who cares, right? Okay, it will not satisfy that, even worse. Okay, so, right. I mean, again, that's my thing. Now, if you include that, that's going to be, okay, so then there is a lot of stuff going on. Just keep in mind that the expectation of these, of the second moment was that. Okay, so this is the frame here. This is the expectation of the second moment, right? And then comes the variance of the sample mean minus the square of the expectation. Okay, I don't care. That's going to diverge too, okay? So who cares? Okay, so I will skipping it. But maybe I'm going to give you an exercise, so then you can check it out, all right? So, and then you can finally practice those things. Anyways, so that's basically what I was using. Again, expectation, let me summarize those things, okay? So the expectation of the sample mean was 0. The variance of the sample mean was sigma squared times n plus 1 times 2n plus 1 by 6 times n. Okay, that was it. That's still going to diverge. Okay, so that's, you know, too big for me. Okay, the expectation of the second sample moment was, again, I'm just collecting those results right now. So it's not new, right? You can see that over here. So I'm summarizing those. Sigma squared times n plus 1 by 2, okay? Now, as you will see, the sample mean does not satisfy the vehicle of flush numbers because its variance is going to diverge. And the variance of the, I mean, okay, that's one of the, how basically we're justifying it. And the second empirical moment will not satisfy the weak law of large numbers also either, because this is going to diverge as the sample size increases. Okay, and that's the point. And that's basically the justification. Okay, but I wanted to have that. So I want to basically, you know, before I make the statement, I wanted to show you what these things are, and I'm going to put those together. Okay, so if there is a drift, of course, the expectation it will basically change. The variance will not. Okay, so the variance will not change, but the expectation of the second empirical moment will become even worse. So in terms of, if I say worse, I mean, of course, in terms of convergence, right? So that is basically, there is a 6 missing. I apologize for the presentation. I hope it's going to be on the slide. I'm not sure, but maybe I skipped that one basically here in the presentation. So there was a 6 was missing. Or even, yeah, 6 times n even, okay, which I skipped here, unfortunately. Anyway, but this is the animated version, so I hope that the rest will work. So, and that's a statement that I'm going to make now. So again, which is referred to as inconsistency. Estimators are called inconsistent if they do not converge in probability to their respective parameter that they're trying to estimate. Okay? So neither does actually the sample mean, nor does the sample variance. I mean, it's time dependent, so why would I basically converge, right? But anyway, I would need to make that statement. Okay? So the sample mean of the random walk, which again is here, does not satisfy the weak law of large numbers. LN stands for weak law of large numbers. Okay, so I'm going to make that statement now. So that's the sample mean of the random walk, right? And yeah, it's going to diverge. So in probability, right? So that's basically what you will have as the sample progresses. Remember what convergence in probability was? Convergence in probability was that the probability, the limit of the probability that actually the sequence of the random variable would exceed its limit will be converging or will be approaching 0. So it's going to be less and less likely that the test statistic will deviate from its expectation, which is not going to be the case here. So it's going to be actually the opposite. Okay, but I need to make that statement. That's also true if there is a drift. Okay, so that's not going to change it. Again, so recall basically what the weak law of large numbers were or was. Okay, so the sample mean would basically converge in probability to its expectation as the sample size progresses if actually the sequence is IID. Now, if the sequence is not IID, that still could do it. Okay, but it doesn't do it, and it's going to be not IID. So that's basically the chain of implications that you would need to address here. Okay, but that's it. Anyways, okay. Now, the second statement I'm going to try to make is that it doesn't satisfy the weak law of large numbers. Sample variance does not satisfy the weak law of large numbers either. Okay, so neither does the sample mean nor the sample variance. The sample mean is the mean of the squares minus the square of the mean. Okay, that's it. And that will not be converging either. Okay, so in probability at least, you know, based on the weak law of large numbers. I'm going to prove that. Okay, so that's going to be a statement, and I was already proving it indirectly because I was looking at basically those expectations and variances and so forth. But I'm going to be more specific here. I will basically look into the expectation of the partial sum process. Okay, so that's going to be the answer. And that is also going to be true in case of the central limit theorem. Okay, now the issue with the distribution is that it could be there could be let's say some sort of a finite distribution. You're going to see the central limit theorem again. That's it. Okay, so this is it. You will see it again. And if you basically do that on the sample mean of the random walk, similarly, okay, I mean, again, if there is no drift, this is what it's going to be, so that's its expectation. But the square root of the sample size times that test statistic will not converge to the normal distribution. So it does not satisfy basically the central limit theorem, and that will be it. Okay, now regarding the distribution, it's not specific. So I'm not supposed to write it basically infinity as, it's not a limit, okay, but that was basically the previous notation, okay, because it's not necessary that, you know, what is an infinite distribution, by the way, okay, so that's not clear. All right, but I can make the statement that it does not converge in distribution, at least not to the normal distribution. That could be another distribution anyway. Okay, so the central limit theorem will not work on the sample mean of the random walk. Okay, it does work basically for a sample mean of the noises, but it doesn't work for the random walk anymore. Okay, but I wanted to need that statement, and that's also going to be true if there is a drift. So again, if there is a drift, it's still true. It's not going to change. Now, the centralization is going to be different because in this case, as you saw, delta times n plus 1 by t was the expectation of the sample mean of the random walk if there was a drift. Okay, the expectation of the random walk was delta times t, okay, but the expectation of the sample mean of the random walk was delta times n plus 1 by 2. Okay, now, anyways, so that centralization will not actually satisfy the central limit theorem either. Okay, so that's basically just, okay, the issue with that. Okay, so again, I'll recall, and I would not need to look at the sample variance because there is no convergence related to the distribution regarding the sample variance. You could make it basically to be, let's say, you know, some t distribution or stuff like that, but if that's only working if basically the variables are normal, and not even asymptotically will basically diverge. So the chi-square distribution comes up with that, but that's not going to be relevant here anyway. Okay, so first off, I'm going to prove it. So how would you basically prove inconsistency? You need to blow up the weak-low Fletch numbers, and there is 3 ways of doing that. Number 1, you need to look at the it's always, the weak-low Fletch numbers is always going to be about the sample mean converging in probability to its expectation. Okay, so there is 3 ways to blow it up. Number 1, you could show maybe that the expectation is not going to be finite, or the variance of those summands will not be finite, or the expectation of the sample mean is not finite. So there is 3 options to blow it up, and if one basically is diverging, then it's not going to satisfy the weak-low Fletch numbers. So that's the reason why I was looking at it. Okay, I'm going to look at the sample mean again, but this time I'm going to break it down a little bit because I need to have the expectation of the summands. Keep in mind, those were actually you can see this over here. This is the partial sum process in the middle. Okay, so those are the summands. Again, let me repeat how would you basically, you could blow up the weak-low Fletch numbers. Number 1, okay, so just basically you understand the point. Number 1, this is the sample mean that you're talking about. You check whether the summands have finite expectations, which there are, so that's not going to be an option here, because the expectation of the random walk is going to be 0. Or, second option might be an option, you check whether the variances of the summands are finite. If they're not, if they're diverging, then there is no way basically for the sample moment to satisfy the weak-low Fletch numbers. Or, this is going to be third option, which is I'm going to apply later on, you check the expectation of the whole thing. Okay? And if this is not finite, then this is not going to work either. Okay, because if that is diverging, it cannot converge. You see? So that's it. So all you would need to do is just to check for, either for the expectation or for the variance of the partial sum process, or for the expectation of the sample mean. Those are the 3 options. And again, if one of the things are basically going to be blown up, there is no way to satisfy the weak-low Fletch numbers. So that's number 1. Okay, so the expectation of the partial sum process is 0. We saw that. The expectation of the noises the expectation of the sum of the noises is going to be the sum of the expectation of those noises, and of course those noises have 0 expectation. So that's basically intuitively clear. Now the variance is going to diverge. The variance of the partial sum process, the variance of a sum, in this case, is the sum of the variances. The variances are equal because the noises are stationary. So therefore, you're going to have sigma squared times t, which is basically the number of those noises. Okay, we saw that, so that's basically what it was. That's actually the variance of the random walk, by the way, right? So I'm just basically recalling it. And as you see, in this case, the first option doesn't work, but the second it does, because that's going to diverge as time increases, you see? So since it's going to diverge, it's not finite. And if it's not finite, as basically the sequence progresses, then the sample mean cannot satisfy the weak-low Fletch numbers. That's it. Okay, so you can simply just blow it up by showing that Either the expectation or the variance or the expectation of the sample mean would diverge. And it does at least one of them. So again, at least the variance does. The expectation does not, but the variance does. So the variance of the partial sum process is not finite. So the sample mean of the random walk cannot satisfy the vehicle of large numbers. Point blank period. That's it. Okay, so it's easier actually to blow it up, right? You see? Okay, because I was proving basically the vehicle of large numbers, as maybe you remember, and that was the reason why I was showing that. I was proving it basically by using the Chebyshev inequality, right? Okay, so, and the Chebyshev inequality, you know, so specific type of variance, and that will converge in probability then. Okay, now if there's a drift, you got even more options. Okay, I mean, I was addressing that as well. So you're not looking at basically these are the sum ends now. These are the sum ends. So either the expectation of those sum ends or the variance of those sum ends need to blow up, or the expectation of the sample mean need to blow up. All three is going to be basically crushed. So here again, if you put it in and you calculate the expectation of that, it's even worse because the expectation will also diverge. Okay, so not just the variance, but the expectation as well. Now either of the two would diverge. Okay, and or you would also have the option for looking at the the expectation of the sample mean as well. Okay, but you don't need to. Again, the variance is the same. The variance is not going to change. Okay, so if it has a linear trend, it doesn't change, and but thus it's still going to be blown up. So the vehicle of large numbers doesn't work anymore. Okay, now I'm going to look at the inconsistency of the sample variance this time, and for that I'm going to show you that the expectation of the second sample moment is not going to be finite. Okay, so we have already seen that basically. So if you look at basically the second sample moment of the random walk, which we have done, and we will again looking at the expectation of that. The expectation of the second sample moment has already been addressed. Okay, so I'm talking about that one. The mean of the squares. And you don't need to take care of the sample variance anymore, because if this is diverging, then everything else will be also blown up. So that's, that's it. So we can, I was doing that already, so I was preparing it. That was basically my job to do it. Sigma squared times n plus 1 by 2 was the result. And that is diverging as the sequence progresses. So if this is diverging, and how come, how would basically the second sample moment would be finite? Or at least, in terms of convergence in probability, it cannot. Okay, it diverges, right? So basically, the expectation does, so it cannot basically keep it up with that. So that's not going to satisfy the vehicle of large numbers either. This is a simple way to illustrating it, okay? And now, how would you establish the vehicle of large numbers? Then you would need to establish three things. Number one, the finiteness of the expectation of the sum ends from which a sample mean was taken from. Number two, the finiteness of the sum ends regarding the variance of them. And number three, the uncorrelatedness of the sum ends. So if these things are met, then you could establish it. Okay, now uncorrelatedness cannot be achieved here, not directly, but you could have at least the weighted sum. But the weighted sum will also diverge, so it's not going to work. Anyway, yeah, so, all right, that's it, okay. So that's it, okay. Sample means and sample variances do not converge in probability, which means that actually those things cannot be used to estimate expectation and variance of a random walk, in contrast to a stationary process, which would work fine most of the time, I think. All right, now if there's a drift, it's not going to change, because again, all that changes is actually, it converges even faster, or diverges even faster, pardon me. Okay, so it diverges even faster. Okay, but it will not be basically. All right, okay. That's it. Okay, so I was basically making that statement here already. Now I'm going to look at basically the violation of the central limit theorem, let's say. So why asymptotic normality doesn't work either, at least not for the sample mean. The sample mean is actually, when you look at basically it, it was there. So that's the sample mean. I mean, the random walk was already here. This is the sample mean of the random walk, so that's already there. Okay, and I was addressing it. So I was addressing it by sigma squared times n plus 1 by times n, 2n plus 1 by 6 times n in the denominator. Now that's going to diverge as well, because you have n times 2n is 2 times n squared. That's the biggest term, so I mean with the biggest exponent, right? And that's going to decide. So the numerator will have order 2 and the denominator will have order 1. So that's going to basically be of order, so I'm not sure if you're familiar with the Landau notation, that will be actually of order n, right? Okay, so you're in this case though. So that will behave just as a linear function in the long run. Anyways, it's going to diverge, okay? So it's going to diverge, and thus, if basically the variance of the sample moment does diverge, then the central limit theorem cannot be addressed either, because it's not supposed to. It's supposed to actually converge, especially to 0, right? I mean, okay, so we're looking at it. So here, again, here comes the statement again, it will not basically work. And that's the reason why I was preparing those things. Okay, so again, I'm going to create an exercise, so I would like you to ask you to repeat those things, so to make them accessible, okay? Right? So that is going to be an important issue. And okay, so that's that. Now, if there is a drift, it's not going to change anything. Okay? Still it's going to diverge because the variance is going to be the same. Okay? The variance will not change if you add basically a drift parameter to it. Okay? So if the variance of the sample mean diverges, the sample mean cannot be basically used for establishing the central limit theorem. Even basically you would, you have a linear transformation of that either. It will not work. Yeah, so again, so then you would need to do another test statistic, right? You could simply just basically take that or the square root of that as a numerator. That would work, but that's not the sample variance and the sample mean, right? So that's going to be another issue. So you could estimate that parameter, but you need to have a different test statistic for that. Anyway, yeah, so I'm going to look at basically the concept before we take a break, and after that we're going to look at the so-called diffusively rescaled random walk. That's going to be a very important issue, okay? Because I'm going to look at further asymptotics with the random walk, which is also involved in here. So rescale means I'm going to change its scale, and by doing so I will simply use a linear transformation of it. So the random walk is actually equal to the partial sum process, okay, in this case. I assume that. Again, you don't need that assumption, but it's just unnecessarily complicated. It's not complicated, but it's unnecessary to neglect it, okay? It's very much, basically, very much easier in that sense. It's not difficult either, basically, if you don't assume it, but you're going to have a little trouble there. Now, you need to understand that, let's say you have a sample of those random walks at time point 1, at time point 2, at time point n. So t, which is the index here, is going to be something from the set containing 1, 2, and n, of course, right? That's obvious. Okay, so far we are done. Okay, now what I'm going to do now is I'm going to introduce another parameter. So the time point that I'm looking at, basically, so how many, people tell me how many sums there are up to this point, is going to be calculated differently now. This means, okay, so I'm not sure if you know these brackets, this is the floor function. I don't know if you heard about that. So floor function is, you should round towards 0. Okay, so towards the nearest integer, basically, towards 0, or so you should round to the nearest integer. So I'm not sure if you know what this operator is. So if you're not, basically, then I'm going to explain. So what is going to be, I mean, this is called the floor function of 3.1. If you should round this towards the nearest integer, what you should basically round it towards 0, that's going to be 3, okay? But that's also going to be true if you have basically 3.9. Because that is also supposed to be rounded towards 0. So if you round it towards 0, that's also going to be 3. You understand what I'm saying? Okay, so whatever comes up, you should basically cut the digits, right? That's it. Okay, so you're cutting the digits. That's a for operator, and there is also the ceiling operator, but I don't need that one. Okay, now it will tell you how many summands you shall include, because I'm going to try to create a continuous time process. So that's the goal. Okay, so time is actually not just discrete points, but you will have also continuous points of time. So after a certain point, there will going to be some change. Anyway, I'm going to define, and that's what I'm going to tell you. So again, so this operator means you should round towards the nearest integer, but actually towards 0. So not basically, actually, I should have said actually round towards towards 0. It's always going to be positive, so let's keep it that way, okay? So you just cut off the digits actually, okay? You know this operator? Now R is going to be the sample fraction. I'm going to show you that one. So that is going to be some value between 0 and 1, and that's going to be a scale parameter, or rescale parameter, you can call it like that. I haven't seen that one, but that's something is going to be 0 and 1. So let's say you do a simulation, and let's say you have a sample of 100 noises. Okay, sample of 100 noises, and then you're measuring this within a normalized point of time, so between 0 and 1. And let's say at time point, so that's also a time point R. Let's say at time point 0.53 or so. Okay, how many observations does that incorporate? Okay, so how many observations you would have? And that will be given by T then. You understand the point? So how many observations you would need to simulate? Let's say this is going to be within a day. Okay, so let's say you have 0 at the beginning and 1 at the end within a single day at 0.53. So that will be around at 12 p.m. something, right? So 0.3 times 60 is going to be, again, 80 minutes. Okay, so this is going to be at 12:18 p.m., right? How many observations you will need to include in there? So in this case, of course, you could actually easily calculate T, because you just need to multiply R times N, and R times N will be actually 53. So that's it. Okay, so that's not going to be a deal, right? You don't need to cut off those digits, but let's say you want to do it a little bit more accurately. So let's say 0.539. All right. So then you will still have basically 53 observations incorporating into that process. But if that changes to 0.54, that's going to change. So there comes another one. Okay, and this is how you would basically you should need to look at it. All right. So the sample fraction will give you the ratio. I mean, let's say you have a time frame which is normalized without loss of generality, so between 0 and 1. So let's say 1 day, 1 year even, 1 year, and then you try to simulate samples from those noises. Okay. And then we're going to look at what happens if basically n is converging to infinity. So that's actually what the issue will be after that. Okay, so we're going to basically look at that one, because the time frame is still going to be between 0 and 1. So the issue will be just you have more and more observations coming in that you could use basically to simulate the process. And then we're going to look at the evolution of the process. Okay, if you basically just break it down. It's not increasing the frequency, although you have basically that as well, but you would rescale the process itself also. Okay, so that's going to be affected by it. If you're not sure, okay, how this works, I suggest basically taking a break now, and then after the break, I'm going to basically address this issue so you will understand the point. Okay, so you can prepare basically just an illustration, so if you make it basically for you to access this issue. Okay, so let's take a break now, and after the break, we're going to continue. All right. Okay, so see you after that. Okay, guys, we are going to continue now. So what I'm going to do is I'm going to show you some paths of this process. Okay, so that's basically what it would be, but I'm going to define it, and then we're going to discuss some properties first. Okay, so you see that what it's going to be. Okay, so by definition, This is called the diffusively rescaled random walk. Again, if you're not sure about that, basically just ignore it for a moment. You're going to see basically how this works. So t is again the time point that you're considering. I will substitute in t by n times r, which is rounded towards 0. Okay, so that basically sign means we round it towards 0 in this case because it's going to be positive all the time. So, or 0 at least, but it's never going to be negative. So we round it towards 0. And basically the parameter r is going to be somewhere between 0 and 1. 1 without loss of generality to normalize it. But that could be also something else, but we will basically just focus on that one. So within basically a fixed time frame. And then you have IID noises, okay, at all points of time. So whether basically it's denoted by t or I or whatever, that is always going to be IID. Okay, so at all points of time we'll have IID noises with 0 mean and constant variances. Okay, so the issue will be not just basically at specific sampling points. Okay, so t would be actually, normally speaking, 0, 1, 2, and so on. But not just all at those sampling points. So not just at point 0, not just at point 1, not just at point 2, and so on, but between those. So between 0 and 1, for example. Okay? And the process will be basically taking the value at point 0. Okay, so that will basically stay there. Anyway, so I'm going to rescale it all the time. But that's basically what it's going to be. And then we're going to discuss some remarks. Basically some properties associated with the diffusively rescaled random walk. Okay, so these are the properties you should be actually aware of. Okay, let me check. It seemed to work. Okay, again, I was just double checking it. Okay, so property number 1, I'm going to address, okay, the issue, what this means. So it's going to be a function depending on r, and depending on n, which is basically the number of noises that are simulated. Okay, so n is basically the sample size of the noises. And the rescaled version of random walk is going to be actually a function of those two. Okay, you can now associate it with r at the time point, basically at the fraction of the sample. So let's say if actually, you know, basically you're considering 1 year as a time horizon. Okay, so r being equal to 0.5 would be actually at after 6 months. Okay, so that's basically it. Anyways, okay, so that is a function of n and r. Okay, you're going to see basically later the pass. The mean of the process, again, is going to be just actually the mean of the random walk, which is 0. It's quite obvious. I will not consider the drift parameter here. So we'll have no drift here, okay? Because rescaling that will be just a different issue. But as you see, the expectation of that is actually the 1 by the square root of n times the expectation of a sum, and the expectation of the sum is the sum of the expectations. And thus, you have basically zeros, all right? Because the noises have 0 mean. So does basically that diffusively rescaled random walk. Now, regarding the variance, I would need to address the variance of the random walk first. The variance of the random walk was actually t times sigma squared, which is actually, you know, time dependent, as you see, so it cannot be stationary, blah, blah, blah. But whatever t is, again, t is somewhere, okay, so it's an element between 0 and n. What you can make sure is that, n could be the largest value that it will possibly take. Whatever the variance of the random walk is, it cannot be greater than n times sigma squared in this case. Okay, because keep in mind, t is always between 0 and n. All right, all the time, including 0. It could be also 0, it could be also n. So whatever the variance is, it's not going to be larger than that. Okay, so that expression, keep that in mind. Now, this means that whatever basically the variance is going to be, again, it will depend on where you would stop counting. Actually, it's not going to be greater than sigma squared times, sigma squared, because now in this case though, so let me stress it because this is the random walk, by the way. So if I say that the variance of 1 by the square root of n times this process here, so I'm talking about that one. I'm talking about that. okay, is addressed, then this is going to be the square of 1 by the square root of n, which is 1 by n times the variance of that. And the variance of that, as you saw, basically is not greater. So you'll basically, whatever that is not going to be greater than n times sigma squared. Okay? So, and that is basically the variance of, or the upper limit basically of that. Okay? So keep that in mind. This is basically the random walk here. So that process, the green one, is technically the random walk, and the variance of that cannot be greater than n times sigma squared. So thus, the variance of the diffusively rescaled random walk cannot be greater than sigma squared, so the variance of the noise. So actually the transformation here, 1 by the square root of n, ensures that the variance of that is going to be at least bounded. You see? Okay, so whatever that is, it's going to be bounded by, actually, by the variance of the noise. You understand that point? Okay, so it's never going to be greater than that. Anyways. All right, so you see, basically, that's it. Now, number 3, the paths are Cadillac. You remember the term Cadillac? Remember what it was? I mean, I cannot speak French, so I don't want to embarrass myself. But this means right continuous with finite or existing left-sided or left-handed limits. You understand the point? Okay, so right continuous. Okay, it's going to be continuous from the right, a right continuous function, so it's a stair function. Actually, it's going to be a stair function, so the paths are going to be a stair function. They're going to look like this. So that the typical Cadillac function, right? They're going to look like, I mean, you'll see them later on, but these are going to be the paths. Okay, well, you have actually a single dot in here, and they're going to be right continuous. Okay, so, I mean, it could be like this. All right, so then it could go back, whatever. So this is it. I'm not saying it is, but it could be, again, so the paths are random, but if basically the randomness component is fixed, then we call it the path. And this is how it's actually is going to be, okay? You see? So it's going to be actually a Cadillac function, okay? You see? Right continuous, because if you come from the right, you always have continuity of the function, right? So if you come from the continuous, it's always going to be the limit of the images is going to be the image of the limit. You remember that? We did this actually extensively. And, but at least, okay, so on the left, it's not going to be left-handed continuous, so it's not going to be basically left continuous. Because if you come from the left, you know, there is a jump. So actually the limit of the image is not going to be the limit, the image of the limit, actually. Because here, for example, let's say if this is point, I don't know, 0.5 or so, the image at that point is over here, okay? And the function clearly does not converge to that. So this is not basically the value to which it converges to, you see? Okay? But at least it's going to be finite. So the function is not going to be continuous. It's going to be right continuous, at least. So the paths are going to be right continuous. With finite left-handed limits. That's a term. So that is a Cadillac function. Continuité à droite, something like this. Limité à gauche. I think that was it. I'm sure. So I don't speak French, but I apologize. Okay. Maybe you do. So I kind of laughing. Is that something you remember? So it's a Cadillac function, and it is a step function, by the way. But it can be also decreasing, not as basically the cumulative distribution function that cannot. Okay, so but actually with respect to R. So that was basically the x-axis was R, right? And R is between 0 and 1, by the way. You're going to see that. Now, almost surely, why? Because, again, okay, if there is paths, you know, the random component is fixed, but you don't know basically how this will evolve, right? So almost surely means with probability 1, by the way. That's that. So, okay, well, this is it. So you can ignore it, by the way. But that's it. Now, the largest jump is going to be, so when you have a sample of those noises, okay, and the first observation of those noises is, let's say, epsilon 1, and the largest is epsilon, no, sorry, the last is the epsilon n. And this is the set of the noises that you have, and you need to pick the biggest one, because those are the increments actually of the process. So the largest jumps are actually the increments of the process, and of course you need to pick one with the with the greatest absolute value, not the largest one, but the greatest absolute value, by the way. But you always have the rescale parameter here as well. So you pick basically the noise with the biggest absolute value and multiply it by basically by 1 by the square root of n, and that's going to be the largest jump, whatever that is. Okay, so if it's a simple random walk, okay, which can only take, let's say, 2 different values, then the jumps are going to be equal. But it can be, let's say, also a standard normal with, you know, a random walk with standard normal increments. So it doesn't specify basically what the distribution of the noises are going to be. It doesn't really matter. You understand that? So you pick basically actually the greatest observation of those noises, and, or let's say not the greatest observation, apology, the greatest absolute value from the observations of the noises, multiplied by 1 by the square root of the sample size will give you the largest jump. Now, as you see, as n converges, n tends to infinity, by the way, this is going to converge to 0. Okay, so the jumps are going to be converging to 0 as the sequence of the noises progress. You see? So jumps are becoming smaller and smaller, right? Or tend to be, I mean, let's say. You understand what I'm saying? So that, by doing so, you can achieve actually continuity, at least at the limit. All right? That's basically what it will be. Okay, so it will not be continuous, but as, you know, the number of noises tends to infinity, it will be at least in the limit, almost surely. Okay, you need to add this up. Anyways, okay, so now the width of each step is going to decrease as well. This is going to be 1 by n. So basically the steps are going to be smaller, and their widths are going to be smaller as well, also, right? You see? So you can see, I mean, that's how you would simulate that. Now, okay, number 4, paths are, in addition, continuous, but not continuous. They are continuous almost everywhere. You remember the term almost everywhere? So basically there is just this means actually from the practical perspective, there are just countably many jumps, whatever that is. So whatever it is, okay, that will be basically the number of jumps in the process. It's just going to be countably many of them. Okay, the number of jumps is always going to be n minus 1, by the way. You're going to see that later on when you look at the path. So keep remember that. That's going to be the number of jumps. Okay, now almost everywhere means actually there is, I mean, no matter how large n is always going to be countably many just of them. Okay, and the length of a countable set is going to be 0 as far as you remember. Okay, so it's not going to be continuous, but it's going to be continuous almost everywhere. Where the jumps are, there is discontinuity, right? But everywhere else is going to be continuity. That's a term, okay? And of course, I need to say this almost surely, because nobody knows what will happen regarding the noises, okay? So what kind of noises you'll get. Anyway, so that would be more correct if I said paths are going to be almost surely continuous. No, paths are going to be continuous almost everywhere, almost surely, but it's, you know, it's not very straightforward to say this. Now, the increments are going to be independent because the noises are IID, right? And the noises are the increments, whenever that basically comes up. These are actually the jumps, by the way, so that's going to be it. And yeah, and number 6, the starting value is going to be actually 0 almost surely. Now, in this case, though, that's the issue why you don't need to assume that, that the starting value of the random walk is 0. Because the starting value of the diffusively rescaled random walk is going to converge to 0, at least almost surely. I'm not sure if you're seeing that. So whenever you're addressing this, okay? Okay, so at point 0, as n tends to infinity, right? You see? You can see that basically what's happening here. I mean, this is equal to actually 1 by n times the random walk, or the starting value at the random walk, you see? And as n tends to infinity, Okay? What happens to the whole thing? That will be actually converging to 0 almost surely. You see? So with probability 1, by the way. That's basically for the limit. So even if the starting value of the random walk is not 0, the starting value of the diffusively rescaled random walk will be at least almost surely. So that's why it's not difficult to justify the issue with the starting value of the random walk. You understand the point? Okay, so z is the random walk, the regular one, and z times 1 by the square root of n is going to be the diffusively rescaled random walk, actually. Okay, but that's the issue we're going to see. So that will converge to 0 almost surely, which means that with probability 1, by the way. Okay, that's not difficult to justify. I mean, the variance of that is going to be finite, so all right, so that's not a big deal. Okay, now I want to look at some paths. Okay, so if you're still not sure what this will be, you're going to see it now. And what I'm going to show you is that I was simulating it, so I was doing that by myself. The noises that I used were the simplest ones that you can imagine. So either there is one step, going up, or one going down, and each with probability of 0.5. Okay, so that's the simplest version of a random walk that you can create. I mean, if you use noises like this, you can address basically what the expectation of the noise is. I mean, of course, it's going to be its weighted sum of its realization, so weighted by the probability. So 0.5 times 1 plus 0.5 times negative 1, which is, of course, 0. So actually confirming that's it. Okay, so the noise will have 0 mean. That's for sure. Is that understandable? Okay. Now, what about the variance? Regarding the variance of the noise, it's going to be the expectation of the squares minus the square of the expectation. And the expectation of the squares is going to be actually the square of the realizations times the corresponding probability. So 1 squared times 0.5 times, plus negative 1 squared times 0.5. So this is basically the weighted sum of its squares. And then you have the square of the expectation, which is actually going to be 0. So that is equal to 1, actually, by the way. So 1 plus 1 times 0.5, so 0.5 of 0.5 is 1. You see? So the variance is going to be 1 this time. All right? Okay. Again, at least for that simulation, I did it 10,000 times. I'm going to show you basically what I got. So check this out. Okay, so you see basically how this will work. Now, first off, I'm going to start by basically, getting n is equal to 1. And the starting value was 0. So there is just one noise here. Okay, that's going to be, so 1 by the square root of 1 times the noise. That's just 1. And that was, I set this to be 0, by the way. So that was basically where the noise was starting at. Okay, at least in this part. Okay, so then there is 2. In this case, you have 2, you see? All right, and there is a jump here. Now, of course, the size of the jump, I mean, it can either go up or go down. It's going to be 1 by the square root of, you can see this over here, 1 by the square root of 2 times 1. That's the size of the jump, right? Because 1 is the increment, so that could be either 1 or negative 1, but it doesn't really matter. The absolute value is going to be actually 1. So as you can see, this is confirming it. Here it is. 1 by the square root of 2 is something between 0.5 and 1, right? So that's over here. Okay, anyways, so now you move on. You got 3, you got 4, 5, 6. Again, I'm rescaling it all the time. So just mind the jumps, guys. They're going to be basically smaller every time I basically increase it. Okay, you got 7. Now it goes up, right? And it goes back down. So again, nobody knows what nobody knows. Okay, so this is kind of alternating here. It's not necessary, but it can happen. I mean, it can go in any direction, you see? Okay, so that's basically what I did. You got 20 of them now. So you got 20 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. You see? And there is 19 jumps. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 19. You see? So you understand why there is actually n-1 jumps if there is, I mean, the size is n, because if you have 20 noises, right, from which basically the partial sum process was generated from, you got 19 increments, right? I mean, of that noises. You see? So 19 change. All right. Anyways, yeah, so I was basically playing that game, and this is what I got. Okay, so you can see basically what's happening. I mean, okay, almost everywhere, continuity almost everywhere, except for those points, right? But that's still countably many of them. Okay, so even though it's 29 jumps, okay, there is countably many of them, but that doesn't really matter. Okay, so this is basically how the process evolves. You see that? Okay, it took me extremely long to get that presentation, guys. Okay, so that was hard, but it was worth it. Okay, so I liked it, but it was as it was moving. It's not moving, so you don't see a movie right now. You see presentation slides. Okay, so just mind you. All right, you see? Okay, it goes. I mean, again, this is what rescaling means. You see, I got 100 of them now, almost. I'm almost there. You see, 99, 100. You see, so the jumps are getting smaller, and they tend to be, and of course the widths of the steps are also getting smaller, right? You see, and that's what rescaling means. Okay, it looks nice. Now I'm going to accelerate this a little bit. Now, again, so this time, okay, I was using 5. Okay, for each step, but it's still visible, right? So basically what you have here until that point, so now I got 200 of them, you see? And then, yeah, it goes on and on and on forever, okay? I mean, you could play that game. Now I got 300, so you see? And as you see, it appears to be more and more continuous, right? Although it's not, so keep in mind, guys, this is a stair function still, right? Okay, so it looks, but it kind of like, I mean, okay, it's transitioning to some continuous time process. Now it's 500, you see? Okay, so maybe I should have done this a little bit longer. I got 550, 600, as you see, 700, 800 now, okay, 1,000 now, so you can see, all right? So I was accelerating this a little bit, and then, okay, I got 10,000, but again, so now I got 2,000 now, so it's not going to change that much. You see, it looks like it was continuous, but it's not. Almost everywhere, except at these points, right? I mean, there is 2,499 jumps, so at 2,499 jumps, there is discontinuity still. But actually, the jumps are very small, okay? So you can see this is 1 by the square root of 2,500 times basically 1. That's the size of a jump, right? It's always 1, right, in this case, because, you know, the noise cannot take, I mean, it's either 1 or -1, all right? So it's basically how it was it. So that's basically the size of a jump. Anyways, okay? So it's going to be very small now, okay, as you see. So the square root of 2,500 is 50, right? So 1 by 50, which is, okay. All right, so now you got 3,000, 3,500, 4,000, 4,500, 5,000, 6,000, 7,000, 8,000, 9,000, and the 10,000. That's the final one. Okay, so I would stop here. Okay. Now, there is actually a statement that I'm trying to make about this, because there is going to be convergence, at least convergence in a distribution. Okay, here is R. So keep that in mind. This is the axis. It's always between 0 and 1. Right? You see? Okay, so at the point R, there is going to be convergence in distribution. And there is going to be asymptotic normality here, because the diffusively rescaled random walk is going to be asymptotically normal as the sample size increases. That's the point. Okay. Anyways, yeah. So, and that's a statement that I want. Now we're going back. Okay. So we're going to, I mean, split it, to tear it apart. Okay. So tear it back down. Okay. A bit quicker. You know, degenerating it. And what I wanted to show you is basically these were not the slides that I was giving you, so I was not providing with you with that. I was providing with this one, Okay, so what I did here is basically, so you take 10, okay, so there is 10 steps now, okay, 10 noises, you see, and then you're rescaling it by just basically squeezing that. So I'm framing that now, and then I'm gonna squeeze it like this, you see? So I was going from here to there, you see? That's basically, you know, how I transitioning it, okay? And in this case, I got 50 observations. So I will complete the process right now. You see? So that means basically you're rescaling it. You understand the point? So that's basically what you got. I didn't give you the movie. I was just giving you, you know, that. So now I'm framing it, and I'm gonna rescaling it like this. You see? So I make it, you know, smaller. And then, you know, I have, in this case, I got 100 observations. Not yet, but here they come. So that comes the rest. You understand the point? So it's not just increasing frequency, guys. Okay? Right? You need to understand this. Okay? So the time frame will stay. Now I'm going to take that, frame it, and I'm going to squeeze it like this. You see? And then I will complete it. Okay? So now I got 500 observations here. You understand the point? Okay? Now take it. Okay, so complete the process, squeezing it, and then frame it again. You see? All right? That's cool. So this is what you got. So I was taking that one, and then, okay, 1,000. So make it that smaller, you see? Taking that, framing it, squeezing it. You see? So I'm going from here to this part. Everybody, I think, understands this, right? Okay, then, okay, I want to complete the process. So I need new noises, right? Okay, I need new ones. Okay, I need new 4,000 ones, which are here now, okay, as the cumulative sum, by the way. So that's a random walk that is evolving around here, but it's rescaled now. Okay, so 1 by the square root of n, that's basically the multiplicative factor by which I'm going to rescaling it. Okay, now taking it, and I'm gonna squeezing it again. So I need new 5,000 noises, basically to complete the sample, and then I got 10,000, and now I'm gonna stop. So I did stop here right now. You see? Okay. Everybody understands what rescaling means in that regard? Okay? So, yeah, and you could go on forever. Now, I want to make a statement about this, okay, from the mathematical perspective, but I think you need to see that. So that's why I spend I spend a lot of time doing this, okay? I want to basically make it also consistent, okay? I would not complete the process right now. Okay, guys, is this clear now? Right, so, okay, understandable. Yeah, and because I want to look at the limit of that. And the limiting process that comes with it, okay, is going to be called the Brownian motion. Okay, so that's basically what it will be. Okay, so that will be the limiting. But I'm going to address I'm going to define the property of that by, I'm going to find basically the process by its properties that I wish to basically you should have, okay? Because I was making a statement about the diffusively rescaled random walk itself, okay? Now, basically regarding the convergence, okay, it's not a convergence in that regard in the classical sense. It's going to be convergence in distribution, by the way, which is the weakest convergence, right? So it doesn't predict basically what's going to happen, but it's, again, so whatever the variance is, it's never going to be greater than sigma squared, never, okay? Because it's actually rescaled, right, you see? So to make sure that it doesn't happen. Anyways, okay, so I want to make a statement about that with the tools that we already know regarding the convergence. And this is called the functional central limit theorem. Okay, so the functional central limit theorem, or AKA the Donsker's theorem, that's basically how I refer to it, Donsker's theorem, is making a statement about basically the distribution of that as you increase the sample size, which I did regarding the paths. So I was doing that already. Okay, so it's not a classical one, it's going to be convergence actually in distribution. So keep that in mind. Okay, so basically the stair function at the beginning would not converge to the final one, but it will converge to the final one in distribution. You understand the point? So it will have the same distribution. I mean, it's not the final one because 10,000 is not over, okay? So, but it's sufficiently large to illustrate it. Anyways, okay, so let basically denote B to be the the diffusively rescaled random walk, which is, again, I will tell you that what it is. You can see it over here at time point r, and r is between 0 and 1, which is the sample fraction. Okay, so that will be basically giving you the sample fraction of the noises, right, that you simulate, and you got 1 by the square root of n times the random walk at time point n times r, where you round n times r to 0, right? That's it. It wasn't me. Okay. Okay, sorry guys. All right. Okay, so again, here is the explanation that you just, you saw previously. R is between 0 and 1. Again, this is normalized actually version. And the noises are IID, to make it simple. You can relax the assumption of the noises being IID, but it needs to be independent. Okay, that's one issue. At least they need to be uncorrelated. Sorry. Okay, noises are uncorrelated, but in addition, they are independent. Because the reason for independency is that the limiting process shall have independent increments. And that's why I would need to use basically independency to achieve that. Now, then, actually this thing will converge to in distribution, to the normal distribution with mean 0 and the variance sigma squared. That's it. Okay, so that's a statement. Now, I want to basically demonstrate this because you saw a specific case where I was looking at basically the sample mean of a stationary, or let's say an IID process, which would also satisfy the vehicle of large numbers, right? But again, that's it. So astonishingly easy if you understand the point, okay? Now, this is a generalization of the central limit theorem because it's not always, okay, so for r is equal to 1, that's going to be the central limit theorem that you're familiar with. I will show you that one. Okay, so at time point r, which r is equal to 1, which is the final one, so that will be the final point, okay? That will actually be the limiting distribution of that random variable at least, okay? But keep in mind, this is convergence in distribution, not convergence in a classical sense, okay? So it will converge to the normal distribution, actually based on the central limit theorem. Although the central limit theorem, the central limit theorem is a specific case of that, it was actually constructed from it. And that's basically the issue here. So it's not just at point 1, but at every point. Okay, so actually, basically, I should have added for all of these r's, okay, which are actually between 0 and 1. Okay, so not just basically at time point 1, but actually for all of them. I should have added this. Doing it right now, but yeah, or at least let's say at the fixed point r. Okay, so for r can be considered to be the time point. Anyway, I'm going to illustrate that. So the case which you were familiar with, okay, where actually that was again. So I was making the statement that the functional central limit theorem is an extension or a generalization, you would say rather, of the classical central limit theorem, okay? And I'm going to show you that one. So if r is set to be equal to 1, okay, the question is what's happening to the diffusively rescaled random walk? And the diffusively rescaled random walk is going to be, okay, so again, so you can see that over here. Okay, so I'm going to put in 1 into it, you see? So you substitute r by 1. Now if you do this, and I did it just here, this is going to be 1 by the square root of the sum. You can check that out. So here it is. So you would take that. The only thing that is missing is r. And since r is equal to 1, that must be also here. That's it. So n times 1 is going to be 1, period, right? And yeah, so here it is. And of course, we need to recall, the central limit theorem. So if you have a sequence of IID random variables, the sample mean of that sequence will converge to the normal distribution. Or let's say the centralized version of it is going to converge basically to this kind of normal distribution over here. So, and that is also true for that one, because what you see here is equal to the sample, this is going to be the square root of the sample mean of the noise as a total. That's it. Why? I mean, you can check why. You can see. So again, I'm going to basically move backwards. So the square root of n times 1 by n is equal to 1 by the square root of n. That should be clear, right? That is without a doubt. So the square root of n by n is going to be 1 by the square root of n. And then times the sum from the first to the last observation. Now, where does it end? N times 1 is going to be equal to n. And if you round n towards 0, right, I mean, you don't need to round it because it's actually natural, you're going to get n. So you have the sample mean of the noise. And the sample mean of the noise will satisfy the central limit theorem because the sum ends are IID and with finite mean and finite variances, okay? And the mean is going to be 0. So if you subtract the mean, which is 0, you find that basically this is actually consistent with the central limit theorem. So what you see is the central limit theorem, okay, applied on the sample mean of the noise. You see? So that is a specific case. Now, in this statement, it's not just only true at time point 1. So not just basically when actually r is equal to 1, but also if r is equal to 0.5, let's say, because then it's also going to converge to that. That's the point. Okay, so there comes a generalization. But you would basically, so even though if you interrupted it, it will still converge, okay? Because you would basically drop it earlier, but it will do. So yeah, that's the point. Okay, so this is basically how the generalization would work. Okay, and I was demonstrating it by looking at the paths of these of that process, so you can see that over here. So the diffusively rescaled random walk is going to converge in distribution. Now the issue is this: we need a limit. You know, we don't have a limit. Okay, that's going to satisfy the properties that actually the diffusively rescaled random walk will have in the limit. Okay, so if I say continuous almost everywhere, but the jump sizes are actually converging to 0, so do the widths, they're going to be continuous at least almost surely, okay, with probability 1. So these are going to be the, I mean, I need to analyze basically what the limit, kind of properties the limit will have. I have addressed this a little bit, not fully, but a little bit at least. And based on that, what I wanted to have, I'm going to create one, which I'm okay. So if I say a stochastic process satisfying that is going to be the limit, or the distribution limit, you can call it like that, the distribution limit of the diffusively rescaled random walk. And that will be the Brownian motion, by the way, so which I call the Brownian motion. You understand the point? So that's it, okay? So again, we need the limit, and we're going to define this basically from bottom to, from top to bottom. Right? Because again, so it must be normal, right? So in the limit, basically this is normal. In the limit is continuous almost surely. The starting value is 0 almost surely. So those are going, and the increments are going to be independent. Those are the properties that the limit will have. You understand the point? And that's the process that I need to which this is going to converge to in distribution. You understand it? So that's how it's done. Okay, so you would need to analyze basically the limiting properties, or let's say large sample properties of this process. Okay, and by doing so, these are going to be the defining properties of the limit that we'll have. Point back plane, and we call that limit the Brownian motion. So that's going to be the distribution limit. Anyway, okay, so that's what comes next. That's going to be the Brownian motion. So in this case, though, I'm going to summarize basically the properties that the diffusively rescaled random walk will have, or you can call it large sample properties of the diffusively rescaled random walk. Okay, so that's how it's addressed too. Okay, and these are going to be the limiting properties of that. Okay, so a stochastic process is simply just call it B by now. Okay, B at time point R, and R going to be between 0 and 1. Without loss of generality now, by the way. Okay, now this is set to be a Brownian motion, okay, if it satisfies the following things. And these, again, so let me repeat that statement. These things are going to be the limiting property, let's say the large sample property of the diffusively rescaled random walk, to which basically it will converge, it will converge to the Brownian motion. That's it. So actually we need to know what we want to have, and then we're basically just defining it, all right? So first off, the starting value is going to be 0 almost surely. I was addressing it, right? So we were talking about it, and I was also addressing it basically in the previous case, right? But I was looking at the diffusively rescaled random walk, okay? So as the sample size increases, basically that was it, okay? So you might remember, regarding the diffusively rescaled random walk, 1 by n times the random walk at time point n times r, where basically n times r is rounded towards 0. Okay, so now as n increases, that's going to be basically converge to 0 at least, almost surely. You see, that's a point. So that is a large sample property, and I want to have that point blank period, because that is what I need. Okay, so it's supposedly be like this. Okay, I hope you understand the point now. Okay, so that is actually philosophical here. Now the second property is that it has independent increments, because again the diffusively rescaled random walk has, and so it shall be that this process shall also have independent increments. Number 3, it shall have continuous paths, at least almost surely. Okay, so with probability 1, because again, when you transition, all right, so let's say the jump sizes will basically converge to 0, at least almost surely, right? And yeah, so again, so 1 by the square root of n times a arbitrary noise, again, let's say the biggest one even, again, it doesn't really matter which one you would take, this thing will converge to 0 almost surely. You see? Okay, so when it comes to large sample properties, again, by n, of course, right? So as n progresses, right, you see that the limiting property will be that the paths are going to be continuous, at least almost surely, with probability 1. Okay? You see? That's actually almost, because these are going to be the increments, by the way. So the jump sizes will basically converge to 0 almost surely. All right, or basically 1 by the square root of n is it. All right, now the process shall be normal, okay, because in the limit there is. And this is supposedly be its variance, r times sigma squared. And now we know why, okay, because it's never going to be greater than sigma squared. So here it is. And yeah, so if basically sigma squared is equal to 1, then the process is called the Wiener process. I'm not sure if you heard about that. The Wiener process is actually a Brownian motion for which basically the variance of the noise is equal to 1, from which basically it was generated from. Okay? Now, the Wiener process is denoted by W typically. All right? So that is a specific case. Now, of course, you can standardize basically the Brownian motion. Okay? So that's basically how you would do it. There is actually an R missing, so, but at point 1, this is basically how you would do it. There's an error on this slide, but I will basically come back to that later on. Okay, so that's basically what you end up with. Okay, so that equation is not true. That is only true basically if r is equal to 1. Okay, but yeah, to keep that in mind. That will be basically the standardized version. I'm going to fix that slide, so I apologize for that. Okay, so that is not true, but actually as you know, you will basically, in the conversions, that will be true. Anyway. So regarding the example, now you can basically assign it to be basically the limit of the random walk. I'm going to fix those slides. Let's say you have a diffusively rescaled random walk, which you already saw. And again, this is a function of b and n, sorry, and n and r right now. So this is going to be 1 by n times the random walk at time point n times r, where n times r is rounded towards 0. Which is actually 1 by the square root of n times the partial sum process up to time point n times r, which is also rounded towards 0. Okay, so that's, again, that's what you have actually have seen. Now, in this case, again, so this is technical. We already know this. T is actually the time point that you're looking at. And the noises are IID. And then what? Then actually, you know, I mean, we saw this. The Brownian motion, okay, converges in distribution to the normal distribution with mean zero and variance R times sigma squared, right? Okay. Well, that's for sure. Now, again, in distribution, that's basically Donsker's theorem right now. So you can see it again. All right, so that's Donsker's theorem. Now, based on that, again, we'll see that the limiting distribution is going to be is going to be captured by the Brownian motion, of course, right? Because the Brownian motion has all the properties that the limit of the diffusively rescaled random walk will have. Not a surprise. Not a surprise, actually, at all. You see? Okay? And yeah, so that is it. Okay? Now, when it comes to this, you can basically see that for here, you got 1 by the square root of, this is basically, 1 by the, it's actually, there is a square root which is too much here, 1 by sigma. It's actually supposed to be 1 by sigma squared. I know 1 by sigma. Sigma, it's a square root, too much missing, too many. I apologize, I need to fix that. So this is actually the standardization, and now this will converge to the Wiener process, okay? Because the Wiener process at time point R, which has the variance R, okay? So now this is correct. Again, I was making a mistake. On the slides, it's not the square root, it's just simply 1 by sigma. But I'm going to fix it, I apologize. So I'm going to update the slides, there was an error there. And that was also the previous part, okay? Now, this is correct now, okay? So I'm going to, do that quick. Okay, now let me just make the statement again. Okay, so that's basically it. Okay, this is Donsker's theorem, by the way. And the thing which is also true, or can be applied to, and this is very interesting. So it's not just true basically for, you got the Brownian motion here as well. So that's, again, following from the definition of the Brownian motion, because the Brownian motion has all the properties, or large sample properties, that the diffusively rescaled random walk has. You should basically keep aware that this is actually distribution here, okay? So it's not only asymptotically normal, it's going to be normal. Now what's interesting is that it's also true for different types of functions which are continuous. And this is based on the continuous mapping theorem. So, I will basically, tell you about it. I was not considering it because I was not using it, but let's say if a sequence of random variables converges in distribution to, let's say, to another or to a limiting random variable, then, so this is the implication, and this is basically what the continuous mapping theorem says. Okay, so CMT denotes continuous mapping theorem. Then the continuous mapping theorem claims that the same thing will be true for the images of the members as well as the limit. Okay, so that's not the statement right now, but that's what it's going to be. If the function f is continuous, at least at that point. So at the point basically here for the limit. Okay? And which is true because the parabola is. You see? So no matter what kind of functions you have, that's always going to be true. For example, for the squares. So if basically the diffusively rescaled random walk converges, then any function of the diffusively rescaled random walk is going to be also converging to the function, actually, or to the image of the limit, if the function is continuous at the point of the limit, which, as assumed, is going to be at all points. Okay? So because the Brownian motion is continuous, at least almost surely. You understand the point? So that's basically what the continuous mapping theorem would say. You can look it up. It's not difficult. That's actually for continuity of a function, by the way. But in the case of, for the limits of or distribution limits of random variables this time. Okay, you remember what continuity was. Okay, so the limit of the images would be the image of the limit. That's continuity. That shall be true again for convergence and distribution. If there is convergence of distribution of random variables according to the continuous mapping theorem, if the function is continuous, which is not a surprise actually. From intuition, it's actually clear. All right. Now let me make that statement again because I want to basically more specific here. So regarding the paths, I mean paths do not converge, but they converge in distribution if you take away the random component, right? So this is basically what we're doing. Okay, here I got, I think that was 10. And here I have, of course, it's not true, but in this case, I got 10,000, right? It's not convergence in the literal sense. It's convergence in distribution. That's what you can choose to think of, okay? So that presentation slide is not correct, but it kind of illustrates the statement that I'm trying to make. And that's basically the point here. Okay, so they converge in distribution. They don't converge, they converge in distribution. That's because, again, the underlying values were coming from random variables, actually. Now, here comes the thing. So again, although this slide, okay, so this image is, again, not correct because even though when I was simulating it, this was already finite. Okay, so we had 10,000, I had 10,000 observations here. And on the left, I got 10. You see? Okay, so that's not going to be so the right-hand side is not going to be the limit. But I wanted to make that illustration here. Now here comes the thing. What the continuous mapping theorem allows you to do is allows you to address even the integrals, which can be interpreted in terms of areas. Okay? I mean, it can be negative too. Okay, so when you take the integral, because that function is also continuous. When you do that, what are you doing actually? Again, you're calculating the area here of the step function. You see? Okay? And there is no discontinuity with that. So that's actually a continuous function. You see? Right? I mean, depending on R, but it will be, okay, a continuous function. And the continuous mapping theorem allows you to do that as well. So not just that basically the processes will converge in distribution to each other, but the corresponding areas that they generate will also converge in distribution to each other. That's a very big statement, you see? That's not a stochastic integral, by the way, although you can simply just say. But if you see something like this, this is just actually the area that the Brownian motion would generate. And that area is random. That's a random variable, you see, which was actually generated from a function of another random variable, which function is continuous at all points, you see? And that's it. All right, so no matter what, it's going to be a continuous function. Okay, so no matter which value, okay, the processes would take, right, here. Okay, so those are the values that the processes, right? The function f, the green one, is a continuous one. Okay, so those are the values here, right? Those are the values. You put that into the function to get the integral. And that's going to be actually a continuous one, even though the processes are not. You see? So that is an implication which I'm continue to use next time. So next time I will look into that again. So Donsker's theorem, it's very technical, I have to admit. And then we're going to look at other limiting distributions as well, maybe, or maybe, I'm not sure. Or maybe we skip that part and we move to stochastic integrals directly. Okay, I'm not sure about that. But I will come back to that later on. Not either in the next or basically in following lectures. Okay, because I want to do more functional analysis. Okay, that's the topic issue. Okay. All right, guys. That's what I planned for today. I think it would be enough. It was a lot. So although I finished earlier, it's still a lot. So we did basically a lot of things. And but next week there is no. We'll skip the lecture. So unfortunately I cannot do it. I'm running out of time. So I have basically other let's say, appointments, whatever. And but in 2 weeks there's going to be one lecture, and that will be basically a lecture until the end. So I basically was checking at the calendar. So thank God I had time, so I'm not running out of time. But the last one, actually we just have 21 doubles, 21 single sessions. Each time we're having a lecture, we have a double session. So there's going to be 10 double sessions, and so 10 lectures plus 90 minutes. That's the plan. Okay, so this is that is going to be consistent. But in the last part, I will not intend to do anything new. Okay, but I will upload exercises, and I will try to come up with the readers too. I'm writing them. I'm not that fast. I was spending the time here basically on the movie that you just watched, but I will spend my time a little bit more efficiently. So not just on basically on the show, but things with more substance. Anyway, okay, so I think it will be fine. Okay, so that was it for today, and we see each other in 2 weeks. Okay, I will keep you posted. Okay, thank you very much. That was it.